Okay, so a bit of a reminder from this time. I guess let me go to our PowerPoint. Okay, a bit review of last time. This time we talk about this idea of orthogonality for abstract vector space. So we see that orthogonal and the geometry can be dependent. Can be defined by this inner product, and yeah, so we get orthogonal basis. We see that orthogonal basis has lots of nice property, and and so we have orthogonal basis. Then coordinates can be calculated in this way. So yeah, so any vector x is a coordinate against the orthogonal basis. You can just take the inner product of your vector with your basis element. Okay? And yeah, so orthogonal basis is really nice. You can calculate the coordinate easily, and also if you list the basis element together, it become what's called orthogonal matrix. And the orthogonal matrix has several nice properties, and I guess the biggest one of them is that because each element of them are orthonormal, then the transpose of the orthogonal matrix is the inverse of the orthogonal matrix. So QTQ equal to identity. And also orthogonal matrix is very nice. If you think about it as a linear transformation, then it preserves length. Means that you multiply your orthogonal matrix on any vector, then this qx, qy has the same inner product as x and y. So orthogonal matrix, we geometrically, intuitively, you can think of it as a rotation on your space. Okay. Yeah. I guess if you go really into detail, there are rotation and reflections. Okay. And yeah. But anyway, those are linear transformations that preserve length. And yeah, and then we have also theorems on those half of orthogonal matrix. So you have A, that's not necessarily a square matrix, then, but we can still have the columns of A being orthogonal, such that the ATA equal to identity. But here A is not necessary. I guess let's go back. So A is not necessarily n by n matrix, so we can have AAT not equal to identity. But the AAT will be projection onto C of A. Okay. Okay. And yeah, and if we have loss A being the matrix that we want to solve least square equation, then because the ATA equal to identity, we have that x hat is just ATB. Okay. And yeah, and also we have orthogonal basis that's this A thing in written in other way. So we have a set of vectors that form an orthogonal basis for S. Then there is an easy way to find a projection onto space spanned by those vectors. That is, you just have so if you have some y you want to project onto this x, then then the coordinate on this subspace is same as what you have before. You take an inner product between y and those xi, and times your xi. Okay, so that's the idea. And we have seen that orthogonal basis is a very nice thing. So we have all those nice property, and in particular, we have orthogonal basis. We see that from this theorem we talk about, there is a very easy way to project onto to find a projection onto an orthogonal basis. And yeah, from this thing, we go to the next part of this chapter. That is a way to finding orthogonal basis. Okay, so we have seen that orthogonal basis is very useful, and now we give a process, a very explicit process that let us find the orthogonal basis for our vector space. Okay, so yeah, so this is this Gram-Schmidt process, orthogonalization process, and usually we just call it Gram-Schmidt process. And it let us find the orthogonal basis. Okay, and yeah, so I guess our process start halfway, so we already have a basis for our space. Then we'll turn our basis into an orthonormal basis. Okay, so yeah, so we use this projection rule. Okay, so we'll repeatedly use this projection rule to turn our whatever basis into an orthonormal basis. Okay, and so this process is nice into the direction. So first of all, it's a very nice process that you can just use yourself. So you want an orthonormal basis, you can use the Gram-Schmidt process. Okay, and but the other way is also this process is a nice theoretical tool. That is just by knowing that this process exists, you know that. You know that you can always find the orthonormal basis for your unit product space, and that's a nice thing. And at the end of the chapter, this section will go back to actually 5.2 and see that a lot of properties that we derive in 5.2 can be explained by just the existence of this orthonormal basis. Okay, and yeah. Okay, so this Gram-Schmidt process. Okay, and yeah. Oh, and here we have one interesting that yeah, and we say that we start with a basis and we will find the orthonormal basis, and here we have something that will stay without proof. That is actually if you have just a set of vector that that you can still, so you have whatever set of vector, you can still apply your Gram-Schmidt process, and at the end you will find the orthonormal basis for the span of your vectors. Okay, so you can just have whatever set of vector, they don't even need to be linearly independent, but you can still run Gram-Schmidt process and you will find the orthonormal basis. Okay, so it's a very nice and powerful process here. And yeah, and the theoretical part is this thing. So the important thing is you will have orthonormal basis. Okay, that's an important theoretical result we got here. Okay, but let's first see the constructive part. So the calculation part of the process of okay, so you get a whole bunch of vectors. How you turn or whole bunch of vectors that form a basis. How do you get the orthonormal basis? Okay. And well, orthonormal, it has two properties. We want everything here has a non-1, so it's normalized, and also we want to be orthogonal to each other. So we start with normalized, so we just take one vector from this space, from this set, and we normalize it, we turn it into a vector of unit length. Okay. So we take x1 and we just divide it by length of x1, we get this u1. Okay. And so this will be so this Gram-Schmidt process is a recursive process. We'll first make a u1 that will have a span of u1 equal to span of x1. Okay. And it's quite obvious because we just take x1 and normalize it. Okay. And obviously, so span of u1 will equal to span of x1. Okay. And I guess here we use a bit of x1 to xn is a basis, so that x1 is another vector 0, so you can normalize it. Okay. And yeah, so yeah, so we get u1. Then we want u2, so we want to repeat process such that the u1, u2 will have a span x1, x2. Okay. And how we do this is that we will find the projection of x2 onto span of u1. Okay. And here is a bit of idea. I guess we should draw a bit more picture. Yeah, I guess it's a bit of a picture here. So we have u1 and x1 in the same direction here. And then geometrically we have another x2. x2 is well, x2 is going to be linearly independent to u1, and so we have a different direction. But now the problem is that x2 is not necessarily orthogonal to u1, and we want everything to be orthogonal to each other because we want to construct an orthonormal basis. Okay? So the idea here is where we want to find the component of x2 that is orthogonal to u1. Okay. And so this is where we want to use the projection. So we will find the projection of x2 onto u1 and subtract that. So this is called, I think this is what we call the P1. So yeah, I guess it's a bit confusing, but it's okay. So P1 is the projection of x2 onto u1. So I guess it's a projection onto the first subspace, subspace, the span of x1, x2. Okay, so P1 is a projection. Then you will take the x2 minus P1, and will be orthogonal to it will be orthogonal to your u1. Okay, so this is how we find the vector that is in the span of x1, x2. And but it's orthogonal to u1. It's this x2 minus p1, and here we draw it as we call it a u2 bar, because this will be about equal to u2. But so if you normalize this vector, you will become u2. We know this u2 bar is already orthogonal to u1, and if you normalize this u2 bar, it will become orthogonal to u1. And u2 bar will be non-zero because excuse me. Yeah, u2 bar will be non-zero because x2 and x1 are linearly independent to each other. Okay. And yeah, so let's see this process actually work out in more algebra. So we define P1, that is a projection of x2 onto u1, and that's done by this thing we said about before. So it has a coordinate equal to x2 inner product with u1, because u1 is already an orthogonal basis for this span of u1. Yeah, u1 is also orthogonal basis for span of u1, obviously. And yeah, so coordinate is x2 inner product with u1, and then we multiply it with u1. And from our previous theorem, because this is the this P1 is the projection vector, so we know that we take a difference between P1 and U1. Take the difference between x2 and P1. It will be this U2 bar. It will be orthogonal to U1. And also, as we say, because x1 and x2 are linearly independent, so this U2 bar should be non-zero, because U2 bar is x2 minus P1. And it's x2 minus something times u1, and so it's x2 minus something times x1. But yeah, but because we have a non-zero coordinate on this coefficient on this x2, so we know x1 and x2 are linearly independent. So you have a non-zero coefficient on x2, x1, then adding them together, usually not be a zero vector. Okay, so we check out that we use x1, x2 is we use that x1, x2 are linearly independent. So once again, we use that all those x form a basis, so that we can find a non-trivial u2 here. And anyway, we have a non-trivial u2 bar is x2 minus p1. And once again, we normalize it, and we get u2. Okay. And yeah, so we find the basis for this span x1, x2. And yeah, so we have u1, u2 is also normal basis for span x1, x2. Okay. And then we continue this, and now we want to find the orthogonal basis for the span x1, x2, x3. Okay, so next step, we want to find u1, u2, u3, and I guess we have already u2, 1, u2, u3 here, and we want u1, u2, u3 to be a basis for span x1, x2, x3. Okay. And yeah, so this is the same thing. We have x3. You will be outside of span x1, x2, because we know x3 is linearly independent from x1, x2. And so you will be something outside of x3 will be something outside of this space x1, x2. and so we want to find the component that's orthogonal to span of x1, x2. And we find this by first finding the projection of x3 onto the span of x1, x2, which is also equal to span of u1, u2. And because the u1, u2 is also normal basis, it's easy to find the projection of x3 onto span of u1, u2. You have a linear combination between u1, u2, and the coefficient being inner product between x3, u1, and x3, u2. Okay, so this is a projection P2. It's easy to find. You have x3 inner product with u1, u2, and because we already know u1, u2, and yeah, x3 inner product with u1, u2, and then linear combination. Then we can find this u3 hat, that's u3 bar, that's x3 minus p2, and we normalize it, we'll find u3. Okay, and yeah, so you see that then the rest of the step, you can see that we do similar things. So we keep finding orthogonal basis for bigger and bigger span. Okay, so we will find the span of x1 to x3, x1 to x4, etc. And in the end, we will find u1 and u1 to u1 it will be also normal basis for span x1 to xn, and yeah, that's the Gram-Schmidt process. Okay, and yeah, we have used and yeah, we have used that x1 to xn is a basis, so that so yeah, we have used that x1 to xn is a basis, so that on each step you can always find a non-zero u bar, and so you can find your un. Okay, and yeah, so that's a Gram-Schmidt process, and we write down the theorem. So the theorem says that if you keep doing this Gram-Schmidt process, you will find the orthogonal basis. Okay, and yeah, so x1 to xn is a basis for inner product space V, and here we are being inner product space is important, because only when you have we are having inner product we can define orthogonal. Okay, so x1 to xn is an inner product space, and because we're inner product, we can define this projection and the normalization, etc. And here we have the Gram-Schmidt process right down in more recursive detail. So the first step is you want to normalize your x1. And you can find your u2 to un recursively by having that the k plus 1 u is determined by the renormalization of this normalized difference between this xk plus 1 and its projection onto this previous uk. Okay, so yeah, so we have this pk, that's a projection of xk plus 1 onto all those previous u. So inner product between xk plus 1 to all those u. So I guess we should mark all those xk plus 1. Okay, and so it's really this xk plus 1. Okay, I don't want to mark this one. Okay, and so it's I guess let's mark this, and note that this is this thing normalized. Okay, so we have xk plus 1 minus its projection onto previous thing, and yeah, because it's xk plus 1 projection, so you have inner product of xk plus 1 with all those u you have find as coordinates, and just a linear combination of those is u, that's pk, and xk plus 1 minus is pk, so intuitively is this picture. It will be the orthogonal component, and you normalize it, it will be the next u. Okay, so you keep doing this k, and so yeah, the k is from 1 to n minus 1, because so this k plus 1 is from 2 to n. Okay, so this is how you find u2 to u1. Yeah, and yeah, so and we have simplified. We have kind of already said the proof. So I guess we say, yeah, I have said the proof of why this is orthogonal basis. because each u we find is a unit and it's also going to each other. And I guess the actual proof part is that we should say why each step you can find. So we have a proof sketch here, so a bit of proof. The only thing we need to prove is that on each step you can actually find your u1. So you want to say all those sk plus 1 minus pk is non-zero. We want all those to be non-zero and also x1 to be non-zero. So proof is the proof part is that because your set of xi is a basis. So if xi is a basis, then we will get ui will be non-zero. I guess we can say those ui bar. So the ui before normalized. So the before normalized thing you can always find because it's just a difference to projection. So all those ui bar will be non-zero because xi is a basis. Okay, and yeah, and I guess we can say it here a little bit because you already see it. So because all those x is a basis, so x1 is not zero, so you can find u1, and because this is a basis, and so whenever you pick the next xk plus 1, this xk plus 1 will be linearly independent to all those u1 to uk. And so that this xk plus 1 minus pk will be non-zero, just like this thing. Okay, so this linear independent part will make sure that, okay, so this linear independent part make sure that this u2 will exist, and also this x3 being linearly independent from x2 and x1 and x2 make sure that the u3 will be non-zero, etc. Or u3 will exist, etc. Okay, so yeah, so that's a Gram-Schmidt process. And I guess here we can say a little bit. Okay, okay, a little bit of a corollary. So two things we want to say here. So first is the existence of the process. Means that just existence of this is a very actually a very powerful theorem theoretically, because it means that every finite dimensional inner product space you can find the orthonormal basis. And yeah, but if it's infinite dimensional, then it's a bit tricky because your basis will be infinitely long, and yeah, we haven't defined what is infinitely long basis mean. Okay. But for finite dimensional space, yeah, we will always find a basis. You can just do this Gram-Schmidt process, okay? Because finite dimensional space, it has a basis, and you can just run your Gram-Schmidt process on your basis, and you will find the orthonormal basis. Okay. And oh, sorry, let me try to adjust this. Be weird. Oh. Okay. Wait. Okay. Sorry. Okay, this is annoying. 1 second. Sorry, not here. Okay, and we should be good. Okay. Now it's louder. Okay, and then yeah, we have something extra. We stay without proof, and so we have. Actually, if just the thing we said before, we have just a set of vector then this process still find the orthogonal basis. Okay, and but I guess here we need to say a little bit. And so if your set of vector is not linearly independent to each other, then you run Gram-Schmidt process. Then when you see, so you will get some zero vector. And when you see the zero vector, you just skip it and don't take it into your orthogonal basis. Okay, so say for example, if your x1 is a zero vector, then you just skip u1 and you start with your x2 as you start with the next vector and try to normalize it. And because your vectors are not linearly independent anymore, and so sometimes it's uk plus 1, you will have this difference be 0. So if you have this difference be 0, then you just skip it and don't have uk plus 1, because that means that this xk plus 1 don't increase your space, don't increase the span of your set of vectors, so you can just skip it and take the next vector and try to find the orthogonal complement, etc. Okay, so yeah, so you can, if your x1 to xn is just a set of vector, you can still run Gram-Schmidt process and you can try to find the orthogonal basis. And so this actually means something. This means that if you run Gram-Schmidt on just a set of vectors, it means that it actually compete with, it's very similar to Gaussian elimination. Okay, so yeah, so this is kind of alternative to Gaussian elimination. Okay, because it also allows you to find a set of vector, find a basis for a set of vector. Okay, so let me say this. I cannot erase this. Yeah, and let's say it's similar to Gaussian, and yeah, to Gaussian elimination. And it's actually we see that it's actually better than Gaussian elimination because well, I guess better in some sense. Better in that you will find a better basis for your space, because the basis you find is also no basis, but also you need to do a bit of HR calculation, because you see here that you need to do this in normalization. Okay, and but anyway, sometimes instead of Gaussian elimination, you want to do Gram-Schmidt, because you think having also no basis is better than just whatever basis you get from Gaussian elimination. Okay, any question? Oh, it's really, oh shit. Let me, okay. Yeah, so it's an alternative to Gaussian elimination. Okay, and yeah, that's a Gram-Schmidt process. And then now let's see an example of this working out. So we have we have a set of vector, and yeah, it's a really like Gaussian elimination. We want to find the orthogonal basis for the column space of A. We know we can do this with Gaussian elimination, but now we try to do this with Gram-Schmidt process. And yeah, let's see whether this is a bit better or a bit faster or slower. Okay, so we have these three vectors, and we want to run Gram-Schmidt process, and we want to find the orthogonal basis for it. Okay, and yeah, and so let's do step by step. And the first step is we want to normalize the first vector. So we have the first vector. It's x1, but we actually call it a1. Yeah, we call it a1 because it's a column vector for the matrix A. Okay, so we normalize a1, and actually don't call it q1 for some reason. We call it q1. And anyway, this is our first orthogonal basis. We normalize a1 with norm of a1, and the norm of a1 we give it a name. We call it r11. Yeah, we call it R11, and it's norm of A1 is this square root of 1 squared, and it's 2. Okay, so Q1 is A1 divided by R11, and this is 1 over 2, 1 over 2, 1 over 2, 1 over 2. Okay, and Okay, it's usually called R11 for some reason, but we skip the part. Okay, so there is some QR decomposition, and if you have an interest, then you can look it up in the textbook, but skip it. There is QR decomposition. That's why this is called R11. So because it's an element of some matrix. Okay, so this is from QR decompose, which we skip. Okay, but anyway, let's try to follow through this grand streaming process. So we normalize and got the first vector, and now we want to find the projection of the second vector onto the first orthonormal vector. So we have a Q1 here, and we want to find this P1, that's projection of A2 onto Q1. Okay. And projection of A2 onto Q1 is this R12, and yeah, so the coordinate A2 onto Q1 is this R12, so A2 inner product with Q1, then it's well, A2 is this vector -1, 4, 4, -1, and Q1 is this vector 1 over 2, 1 over 2, 1 over 2, 1 over 2. And so it's this thing adding together and divide by 2. So you have a 3 here, 3 here, adding together divided by 2 is 3. Okay, so the coefficient is 3 here, and it times Q1. So it's 3 times Q1 is 3 over 2, 3 over 2, etc. Then yeah, so this is a multi-step calculation. We are only onto here. Then now we can calculate the A2 minus P1. So A2 minus P1 is -1, 4, 4. -1 minus this 3 over 2, etc. So it's yeah. Then now this is just subtraction. So it's -5 over 2, 5 over 2. Yeah, 5 over 2 and -5 over 2. Okay. And finally we got this, and we can normalize this vector, and it's 4 times this 5 over 2, and you have 4 minus 2 here. For 5 over 2 here, so it's 5 over 2, 5 over 2 times the square root of 4, and it's 5. Okay, so norm is 5, and you normalize it. You see that we have set up the number nicely. We don't get square roots. If we have an arbitrary number, you can expect you got lots of square roots. But this nicely set up example, we see that it's -1 over 2, 1 over 2, 1 over 2, and -1 over 2. Okay, so this is our Q2. And finally, we have our Q3, and we want to find the projection of our X3 onto our A3 onto Q1 and Q2. Okay, and so we have Q1, Q2, and now we want Q3. And Q3 we want this A3 minus P2, and P2 is the projection of A3 onto Q1 and Q2. And well, then we have this R13, so it's A3 on Q1. Okay, and A3 on Q1, then once again we do this inner product, so A3 is we actually write, I think we actually write this inner product in the other direction for some reason. Okay, and yeah. So here, what do we actually write? Although inner product is symmetric, so it doesn't matter. So we have this Q1T on A3. So A3 is this 4 minus 2, 2, 0. Okay, and the inner product with this 1 over 2, 1 over 2, 1 over 2, 1 over 2 is those adding together divided by 2, so it's 2. And then we have S3 inner product on Q2, and Q2 is 1 over 2 with -1, 1, 1, -1. So it's this being minus, and this is plus, plus, and minus. And so this will cancel each other, so you have -4 times 1 over 2, and it's -2. And yeah, so we have those two coefficients, and we can multiply on Q1 and Q2 and adding together. So on Q1 and Q2, so 2 on Q1 and -2 on Q2, and adding together, we see that the middle part we have this plus and the minus cancel out. So we only have the first two parts, and this 1 plus 1, so it's 2 here, 2 here. So A3 minus P2. Okay, so this is P2, and there are many steps. So we only on P2, then we need to have A3 minus P2. So A3 minus P2 is A3 is this thing, and minus P2, and so it's minus 2, 2 here, and minus P2, then you have 2 here, and minus 2 here. Then, yeah, so you see it's 2 times 2 times this 1 minus 1, 1 minus 1, and then you normalize it, it will be, once again, a whole bunch of 1 over 2 is 1 over 2 with 1 minus 1, 1 minus 1. Okay, and yeah, so those are all our vectors here. Okay, and yeah, so this is other Q1, Q2, Q3, and yeah, here we define more of our R here. So Q1 is our R11 divided R11. So we have R11 being the normalized of this A1 bar, the norm of this A1 bar being R11, and R22 being the norm of this A1 minus P1. Okay, I guess we should say here. So R11 being the norm of A1, and R22 being the norm of A2 minus P1. And R33 equal to the norm of A3 minus P2. Okay, and yeah, so all those Rij will form a R matrix, and once again, it's something nice that you can write in QR decompose, and yeah, but we'll skip that, and but you can see kind of here that. All those Q number and R number, they will multiply nicely back to all those A vector. A1 will be R11 times Q1, A2 will be R22 times Q2, R12 times Q1, etc. Okay, so yeah, so you can write your A matrix equal to some Q matrix times R matrix. That's QR decompose. Okay, but we skip that. And we want to know here. We just kind of want to know that we have this. Yeah, this is an example of finding orthogonal basis for A is also a basis for A, and you can judge by yourself whether this is easier or harder than Gaussian elimination. I think it's I don't know, maybe less addition. But there's a lot of square root you need to do when you do this Gram-Schmidt process. Yeah, I think in terms of big O notation, it's probably same as a Gram-Schmidt process, same as Gaussian elimination. Probably, not sure. It's maybe n cube. But yeah. But in terms of keeping track of number, a lot of time you take a square root, so maybe not so nice if the problem is not set out nicely. Okay, any problem on this Gram-Schmidt process? Yeah, but I think the idea is quite intuitive. You just take the vector one by one, and you normalize it. And you take the orthogonal component and you normalize it, and you take another vector, you calculate the orthogonal component and you normalize it, and well, there is a lot of calculation on this orthogonal component, so we need to keep calculating the orthogonal component on the previous span, on the previous space, and taking the difference and normalize it. That's what you keep doing in Gram-Schmidt process. Okay, and in the last 8 minutes, let's talk about a bit of going back to chapter 5 or section 5.2. Okay, so section 5.2, we talk a lot about those orthogonal complements. Okay, And now we know this next property also about orthogonal basis. We can kind of prove things in section 5.2 in easier way. Okay, so now we know every vector space or subspace or vector space, we can find the orthogonal basis for it. Okay, and now we can prove this theorem 5.2 very easily. Okay, so we have a space and it's orthogonal complement, and I guess we still need to say, we still need to kind of from previous thing to show that they have the same dimension. Okay, but once we have the same dimension, then we have some nice thing to say about this S and S dual. Okay, so this if S we know S and S perpendicular, they have the dimension added R to the n, then we can find the orthogonal basis for S, and we can find the orthogonal basis for S perpendicular, and then we see that we release those two bases together, they will become an orthogonal basis. Okay. Okay. Yeah. Oh, I guess here we have actually full proof here. So yeah. Okay. So we can actually use the orthogonal basis to prove everything here. So we say we find the orthogonal basis for S and orthogonal basis for S perpendicular, and for some up to some total number of basis elements being K. Okay. And then because S and S perpendicular are orthogonal to each other, and so this set will be orthogonal. Okay. And I guess we are still missing something. Okay. Did we say? Yeah. Here I guess we are missing something. So from the orthogonal property we know that everything inside here are orthogonal, so the set is AOI. But I guess we are probably missing a bit here because let me think. Yeah, we probably still need to say that we have actually an element here. So we need to say an element because we need to say space and its orthogonal complement. We need to say the span everything. Okay, we need to say the span B. Okay, and I guess it's a bit of a question mark. Okay. And we'll think about this a bit later. But anyway, here we see that 5.2.2, if we are in, this kind of proof only work when you have inner product. So we need to say we are a dimensional inner product space. Okay, then we can have this orthogonal basis view. We can find the orthogonal basis for S, and the orthogonal basis for S perpendicular, then they together will have an orthogonal basis. Okay. And and I guess here is the proof. We need to say what happens when k less than n. Okay. And if k less than n, then we need to find things more. Okay, so there is something. Okay, so we need to. Sorry for the reordering. Okay, so if k less than n, then we can use. So this is actually a nice argument to know. If k is less than n, then we can also find. So this is similar to something we do in 5.2. Okay, so so if our basis don't span everything, then there is something outside of our basis that is linear independent to what we have. Okay, so suppose we find this basis for S and the basis for S perpendicular. So from U1 to UK, and if we don't have a full dimension, and yeah, so I guess here is actually in next page. Okay, so I will fix that later. Okay, and yeah, we can find this xk plus 1, and then by Gram-Schmidt we can make this xk plus 1 into uk plus 1 that's orthogonal to everything. Okay. And okay, so now we can use the property that S and S perpendicular are perpendicular to each other. So UK plus 1 is orthogonal to this basis, this orthogonal basis for S. So it's perpendicular to everything in S, so it's in S perpendicular. And but UK plus 1 is also orthogonal to everything, this orthogonal basis for S perpendicular. So yeah, so I guess I cannot say it's not in S perpendicular. I need to say here we need to be a little bit careful because it's let's say something nicely, okay? And yeah, let's say this I guess it's okay-ish, but what's going on? I think I like to write this as another way. It's more symmetric. So let's say it's orthogonal to everything in S perpendicular. So UK plus 1 is inside S, okay? And because it's both inside S perpendicular and S, then we have that UK plus 1 must be the 0 vector. Okay? But the 0 vector has non-zero, it cannot be normalized. And then it contradicts that UK plus 1 is a unit vector. Okay? So its length will be both 0 and 1, so that's a contradiction. So we know that k cannot be less than n. And yeah, so U1 to UK must have n vectors, and so we have two conditions, so we don't use that is AOI. By theorem 5.1 is linear independent, and next page we have that k equal to n, and so that this is weaker proof of theorem 5.2.2. We say that on any inner product space, we have that S and S perpendicular will add up to dimension n, and they will have this orthogonal basis for each other, and then use this together, it becomes orthogonal basis. Okay, and yeah, I think we are going a bit over time. But yeah, you can see also all other things can be nicely explained by this orthogonal basis. So this direct sum means that the same thing. So U and V have a direct sum means that you have orthogonal basis for U, orthogonal basis for V. They together become orthogonal basis for W, and yeah, then you have the other thing. Okay, and yeah, so that's for 5.6. And this is the end of our chapter 5. We see that, yeah, we have seen this geometry for vector space, and we have an inner product. We can find the angles, and yeah, we can use this orthogonal basis to find a lot of nice things. Okay, so and our next class, we will change to chapter 6 and start talking about eigenvectors. Okay, so let's take a 10-minute break. Okay, let's get back. Okay, and sorry, a bit of a hello. Sorry, a bit of a correction from what we just said. And so this modified syndrome 5.2 is actually more general than what we talk about in section 5.2. Because in section 5.2, we will only talk about Rn. Okay, so we were talking about this theorem for Rn and it's being a subset of Rn. Okay, and here we are talking about this orthogonal complement for general n-dimensional inner product space. Okay, and we see that personally, I think this is actually a more elegant proof than what we have in 5.2.2. Because yeah, in 5.2.2 we were using rank nullarity theorem, but you see here in this proof here we actually don't need to use the rank nullarity theorem. We basically just use basic properties of inner product. We use Gram-Schmidt, and which just says that well, you can find the vectors and you can normalize vectors and you can do projection on your vectors, etc. Okay, so yeah, this is an alternative proof to 5.2.2, and it's more general and don't use rank nullarity theorem. Okay, and then we can use this view and reprove everything in 5.2.2. And yeah, actually all those theorems we should say is modified. So all those are modified because it's more general than what we have in 5.2. So let's mark it as a mod. And let's spend a little time to go through this a bit carefully. Okay, and so this definition of direct sum is actually the same as in 5.2, because in 5.2 we were able to use this, but yeah, because it's only a definition, this is actually a definition on general space. So yeah, we can still use this direct sum. Okay, and actually direct sum don't need to be on inner product space, and yeah, so it's a bit weird from all the things we said about here. But yeah, so you can define this direct sum here. So you have a U and a V, and so basically direct sum means that direct sum means that you have the direct sum actually don't need the inner product. So let's take a note here. So although the section are about inner product, this direct sum definition don't need inner product. Don't need the inner product. This is more about definition on linear independence, a concept on linear independence. So this don't need things being orthogonal. Okay. Okay. And so basically, direct sum means that the basis of U and the basis of V together will become basis of W. Okay. And anyway, so with this our modified theorem 5.2.2, then it's pretty straightforward to prove this modified theorem 5.2.3, and so we have if S is a subspace of so now here we need to say a lot of long string of things for RV. So V is a finite dimensional inner product space, because only on inner product space we can define orthogonal. So we will have this orthogonal complement. Okay, and yeah, I guess we skip the definition of orthogonal complement for general inner product space, but it's very similar to what we have in Rn. Okay, so this S perpendicular for general inner product space is just whatever collection of things that perpendicular to S. Okay, so finite dimensional inner product. I cannot spell this. Inner product space. Okay, and yeah, and then we have S and S perpendicular. Then V will be equal to S and this direct sum with S perpendicular, and it's almost immediately from our 5.2, we say we find the orthogonal basis for S and the orthogonal basis for S perpendicular, and then we just list them together. It will become orthogonal basis for our V. Okay. And yeah, that's almost immediately to the to this direct sum definition, because then we find everything in V, then we can find then we can find its coordinate in this U1 to U1 basis. Okay. And yeah, so we can write because U1 to U1 is a basis for for V, then everything in V can be written as some linear combination of U1 to UR and linear combination of UR plus 1 to U1. And here we even know how to calculate the coordinate very easily. We know it's just you take the inner product between V and all those UI. Because here it should be V. Okay. So Ci, let's just rewrite. So all those Ci should equal to inner product between V and UI. Okay. And and yeah, so we find those coordinates. Then we see that the first part in S and sorry, I guess I messed up. So I have a W equal to U plus V, so actually W here. And yeah, sorry for very confusing here. So this is actually W here. So we have a W and a UV. We want the W equal to U plus V, and so this is W, and this is Ci, and yeah, Ci equal to W inner product with UI, and so W equal to U plus V, W equal to U plus V, and yeah, so this is existence, and uniqueness we can do similar to previously to this proof, but uniqueness basically comes from, well, this is a basis, and U1 to U1 is already a basis, and you write so all the UV in terms of this basis is basic unique. Okay. And yeah, so that's 5.2.3 proved by having this Gram-Schmidt process. And then we can also have 5.2.4 reprove again. So this is also modified 5.2.4. This is for, once again, general vector space V. And so we say that we can also prove S perpendicular back to S by just looking at the orthogonal basis. Okay. And now we just need to look at the orthogonal basis for S. Okay, so suppose we have U1 to UR, that's the orthogonal basis for S. Okay. And then this orthogonal basis, we just need to say it's a basis for, also a basis for S perpendicular. And first it will be, every one of them will be so they will be linearly independent because it's a basis, and also it's inside as perpendicular because well, obviously every one of them is perpendicular to things in its perpendicular. Okay, so we have these two conditions. They are linearly independent, and inside is a double perpendicular space, so it's a basis for it, and yeah, so this thing is has the same basis for as S, and so it's the same space. Okay, so yeah, hopefully this gives us let you have a better view of all those weird direct sum and perpendicular theorem we have in 5.2, and now it's in more general version. It's in any inner product space. Okay, and so yeah, I guess here we should also have technically we should redefine this as perpendicular for general inner product space, but yeah, but let's just say define as perpendicular similarly, and I guess I will update the slide later. Okay. So define it similarly as in 5.2, but on general inner product space. Okay, so that's yeah, a bit over time, but that's the end of our chapter 5. And yeah, chapter 5 is about orthogonal, and we see that being orthogonal can be defined by inner product. So yeah, most important thing in this chapter is we have y perpendicular with x. This means x inner product with y equal to 0. Okay. And everything comes from here. Okay, and on the next half of the class, let's try to do a bit more progress, and let's go to chapter 6. Okay, hopefully our online thing is still active. And let's go to chapter 6 and totally switch gear to this is stuck. Totally switch gear to a different thing. Okay, so yeah, I guess while PowerPoint is saving, I shouldn't close that. Take a really long time to save. Okay, while PowerPoint to save, let's talk about a little bit. I guess let's talk a bit about. I think people should learn. From what I recall, eigenvalue and eigenvectors are taught in high school, but let's take a vote. So, how many of you have learned eigenvector and eigenvalue? If you heard about it, okay, learn about it, raise your hand. Eigenvalue and eigenvectors. Actually, no. If you haven't heard about it, raise your hand. Really? Okay. Okay, and then let's do it a bit slowly. Okay, so yeah, eigenvalues, and I guess we actually talk more than eigenvalues, but yeah, we also talk about singular values, but it's kind of similar to eigenvalues. Anyway, we have in chapter 6, the most important thing we talk about are those eigenvalue and eigenvectors. And we will skip chapter 6.2 because it's more on applications. Okay? We focus more on fundamental theory here. And but anyway, on 6.1 we talk about eigenvalue and eigenvectors. And in this section we are doing, I guess, more like a matrix analysis. Okay, so yeah, we focus on matrix, and we want to analyze the properties of matrices. Okay, and yeah, so eigenvalue and eigenvectors. So we start with n by n matrix. So eigenvalue and eigenvectors only define on n by n matrix. I guess this is kind of important. You only define on square matrices. Okay, and but anyway. It's important to know it's on square matrix, but then we don't use too much about this n by n now. Okay, but anyway, so what are eigenvalue and eigenvectors? I guess intuitively is we want to analyze A as a transformation. Okay, so here, so we want to think about a matrix as a linear transformation. And we want to see how A do as a linear transformation. Then eigenvalue and eigenvectors says that this linear transformation has a special property, so that yeah. So for every matrix A, you can actually find yeah, I guess there will be some number of eigenvalue and eigenvectors. Hopefully there are n, but sometimes we will get bad matrices. But that's a bit of a later part. But let's first have this nice property. So we want to see A as a linear transformation, and sometimes we will have a very nice linear transformation. And I guess here we use the n by n part. Okay, so it's A is an n by n matrix. So I guess we should not say linear transformation. So here we should use more precise, and we should say it's a linear operation. Okay, operation. Okay, So A is an n by n matrix, so it made map a linear vector from a linear space back to the same linear space. And so sometimes we can get lucky, so we use A to transform a vector, and it will back to the same vector but with same length. Okay, and so we write down this as a matrix vector multiplication equation. Is just Ax equal to lambda x, and so lambda is a scalar and x a vector. And so the definition of eigenvalue and eigenvector is very simple. It just says that wherever you have this thing happen, then we say x is an eigenvector for A, and lambda is eigenvalue for and then lambda is the eigenvalue for A. Okay, so lambda is the eigenvalue or characteristic value, and x is an eigenvector or characteristic vector. And we will say x is belonging to lambda or correspond to lambda, etc. Okay, and yeah, so that's the idea of eigenvalue and eigenvector. Is some very special. Yeah, eigenvector is a very special vector under this linear operation of A. You get this x get operated by A, and you go back to the same x, but maybe with some multiplication. And yeah, let's see some examples. So A is this matrix, and x is this vector. Then we do matrix multiplication, and we see that it's 3 times x. So this 3 is eigenvalue of A, and x, this 2, 1 vector, is the eigenvector that corresponds to this lambda equal to 3 eigenvalue. Okay, and then from this example, we see that because this multiplication is linear, then we see the first property about eigenvector is that you can have any non-zero multiplication of x, and you will be eigenvector. So because A times alpha x is alpha times ax, and you have the same eigenvalue, you will be lambda times alpha x. So it's alpha times lambda x and lambda times alpha x. Okay, so alpha times x with any non-zero alpha will be also an eigenvector, but it will have the same lambda here. And from now on, we will basically think alpha x as the same eigenvector as x, because really have the same property corresponding to same eigenvalue. You just multiplying by some vector. So when talking about eigenvector, we only care about the direction, and multiplying by some alpha doesn't really change the property of this eigenvector. Okay. Yeah, and yeah, so that's the eigenvalue, and yeah, here we want the vector x to be non-zero vector, because obviously you have A multiply on the zero vector, only just be a zero vector times any eigenvalue, and it's not very useful. Okay, so also need to remember it's a non-zero here. And yeah, we can have see the example here. So we multiply x by 2, it become 4, 2 here, and A times x is this 12, 6 is also 3 times 4, 2, and it's 0, 3 times x. Okay, and so far it's about multiplication of eigenvector, and then now we start solving for eigenvalues. Okay, eigenvalue and eigenvector. So how we solve for eigenvalue and eigenvector is we think about this equation. Okay, so we know, well, eigenvalue eigenvector satisfy this equation as A is equal to lambda x, and this is a linear equation. You can move things around. You have x minus lambda x equal to 0, and lambda x equal to lambda times identity times x. So we can write A minus identity times lambda. Then this this complicated matrix together times x equal to 0. Okay, and so we have that if lambda is the eigenvalue for A, then only if this equation has a non-trivial solution. And then we can go back to go back to our favorite theorem. This is theorem 1.5.2, and it says that this is a non-trivial solution if only if well, this thing is singular, and means that yeah, so this eigenvector is the null space of A plus lambda I, and excuse me, and 1.5.2 says that this is non-singular, and yeah, yeah, oh sorry, 1.5.2 says that I guess I should put it here. So 1.5.2 says that this is a singular, and in chapter 2 we know that means this means that the determinant of A minus lambda I must be 0. Okay, and so this equation determinant of A minus lambda I equals 0. This is as the equation of so here we think lambda as unknown, lambda as I guess as a variable. Okay, this equation of lambda is called the characteristic equation for matrix A. So basically, we need to solve this equation to find the eigenvalues. Okay, and but back to this analysis. So if we have A minus lambda has a non-trivial solution, then it has a non-trivial null space. Okay. And so this so okay, and so I guess the logic actually goes a bit weird. Okay, so when we solve an equation here, we think lambda as a variable. Okay, and so this will be a polynomial for lambda, and then we solve yeah, I guess let's talk about this solution first. Okay. So we want this thing to have a non-trivial solution, and sorry, we want this equation to have a solution, and this equation as the equation for lambda. Then you can expand out this determinant. We will see that this will be a n-degree polynomial for lambda, because you just expand out this determinant. You have the recursive definition for your determinant. You see that it is nth degree polynomial for lambda. Okay, and this is called a characteristic polynomial. We have this it's hard to pronounce. Characteristic equation. It just says that the characteristic polynomial is 0. And the roots of this polynomial will be the eigenvalues of A. Okay, and so now we think you need to use a bit of I guess analysis. We have an n-degree polynomial, and we want to say how many roots do we have, and you will have n complex roots. So we calculate the eigenvalues. And here is actually the only part of this course that we really care about complex number, because on eigenvalues we really like complex eigenvalues, and because when we solve polynomials we will have complex roots. Okay, so eigenvalues will actually take care of complex numbers, because we will have n complex eigenvalues. Okay, and anyway we'll have those n complex eigenvalues, and now we can back to think about this null space. Okay, so we solve for those n eigenvalues, and now we excuse me, we fix those eigenvalues back to this equation. Now we want to solve for our eigenvectors. So yeah, so when we have this characteristic equation, lambda was a variable, we can solve for lambda. And once we solve for some fixed lambda, we can think about the null space of A minus lambda. Okay, so when we think about this, we are kind of fixed lambda. Okay, so I guess the logic ordering is a bit weird. So we'll solve equation, and now we fix lambda. Okay, so in this we fix lambda, and fix the lambda we can think about the null space of A minus lambda I. Okay, because A minus lambda I is just now a fixed matrix, and this fixed matrix we know it has some null space, and well, then we can find it, and yeah. Yeah, so here is the fixed lambda part. Okay, so we fix eigenvalue of A, and we have a non-trivial null space, and anything inside the null space will be, I guess, any non-zero vector inside the null space will be eigenvector of lambda. And so this null space is called eigenspace correspond to lambda. Okay, and yeah, so here is another definition is the eigenspace. Okay, so yeah, sorry for this kind of weird ordering. And yeah, so here is a basic of already outlined to how to find the eigenvalue and eigenvectors. Okay, so summary of what we learned. So we have n by n matrix, and here are a bit of equivalence statement between eigenvectors. So A is the eigenvector and the eigenvalue. So lambda is the eigenvalue of A. Then A minus lambda ix will have a non-trivial solution, and this means that determinant of A minus lambda I must be 0 because this is singular. Oh, I guess we go to here first. So this is 1.5.2. And so this means that A minus lambda I is singular, and this means the determinant of A minus lambda I must be 0, and this also means that the null space of A minus lambda I is non-zero. Okay, so these are equivalent things, and yeah, so we will use this property. So this one is the most useful one because it's just an equation for lambda. And we'll use this to solve for our lambda. Okay, and yeah, so now let's find the eigenvalue and the eigenvectors in this example. So we have A equal to 3, 3, 2 minus 3. And yeah, let's write down this equation. Let's first write down this matrix A minus lambda I. So A is this matrix here, and A minus lambda I. So basically on the diagonal elements, we have minus lambda, and we want to calculate the determinant, and say it's 0. So determinant of 2 by 2 matrix is easy. You have this times this minus this times this. So 3 times lambda times minus 3 minus lambda times minus 2 minus lambda minus this 3 times 2 equal to 0. And expand everything, and should be lambda squared minus lambda minus 12 equals 0. So we have a polynomial here, and we solve this roots of the polynomial. We want to factor it. It's lambda minus 4 times lambda plus 3 equal to 0. So lambda 1 equal to 4, and lambda 2 equal to minus 2. We have two distinct eigenvalues here. So 2 degree polynomial, we have 2 roots. And as we say, now we fix lambda as different roots here, and we want to solve for the null space of A minus lambda I. So fix lambda equal to 4. We have A minus 4i, and this is 3 minus 4, and minus 2 minus 4. And we want to solve for null space, and for solving null space, we do this quite a direct thing. So we have just write down the equation and have it multiplying on x equal to 0. So it's minus 1, 3, 2 minus 6, x1, x2 equal to 0. And then to solve this, we can do Gaussian elimination again, but actually usually it's quite easy to just eyeball the solution here. And but I guess yeah, so for null space we have done this multiple times. You want to be careful. You can do Gaussian elimination, and yeah, but here we can just eyeball this. We see that you have x1 equal to 1, and then x2, or I guess here we say x2 equal to 1, then because minus 1 x1 plus x2 equal to 0, then we can just have, yeah, because here we have -1 minus x1 plus 2x2 equal to 0, then we just have x1 equal to twice x2, and it's as 2 alpha alpha. And yeah, so our eigenvector is whatever alpha here multiplying on this 2, 1. Okay, so eigenvector corresponding to 4 is this 2, 1. And then similarly, when lambda 2 equal to -3, we can do similar thing. Okay. So null space of A of actually plus 3i here. So 3 plus 3 minus 2 plus 3, then we have 6 and 1 here. So 6, 2, 3, 1 here. And once again, it's pretty easy to see. So we have x1 equal to 1, x2 should equal to -3 because we have 3, 1 here. And so minus alpha and 3 alpha. And so alpha times -1, 3 is the eigenvector. Okay. So any question about the calculation of eigenvalue and eigenvector here? So yeah, so this is a calculation you will do a lot in your homework and exam, how to calculate the eigenvalue and the eigenvector. Okay, and now let's see a bigger example, and it's pretty similar. So A equal to this 1, 2, 1, 1, and -3, -2, -3, and 1, 1, 2. And once again, we want to calculate determinant A minus lambda I. So you put a minus lambda on your diagonal, so you have this determinant of A minus lambda I here. So it's just A and minus lambda on determinant. And yeah, then you need to do a lot of calculation. You can see the handwriting here. You do all the calculation and factor it. You see that the determinant is this polynomial on lambda is degree 3 polynomial on lambda is minus lambda, and lambda minus 1 square equal to 0. And yeah, we have once again 3 roots of this polynomial is 0, and now we have something special. We have a double root. We have lambda 2 equal to lambda 3 equal to 1 here. Okay, so now we have a different case. We have 2 roots that are actually equal. So lambda 1 equal to 0, and lambda 2, lambda 3 equal to 1. Okay. And the first to deal with this single root here is simple. And yeah, A minus lambda 1 I equal to 0. Lambda 1 was 0, so it's just AX equal to 0. And AX equal to 0. And well, it's now 3 by 3. It's a bit harder to eyeball the null space, and we do Gaussian elimination. So yeah, so once again, we pull out our augmented matrix. So A and 0 here, and we do Gaussian elimination. We see that this matrix, we turn A equal to this REF. So, and we see that we can turn it to REF. Then we can have alpha A3 as a free variable, and we see that x1 x2 equal to this both equal to x3, and yeah, x1 x2 both equal to x3. So x1 x2 x3 just alpha times 1 1 1. Okay, and that's the eigenvector correspond to lambda 1 equal to 0. Okay. And for lambda 2 and lambda 3, they have the same eigen, they are the same eigenvalue, and so they should share the same eigenspace. Okay. And lambda 2 equal to 1, so we have A minus lambda 2 equal to A minus lambda 2 identity, and it's equal to this matrix 1 1 1 minus 3 minus 3 minus 3 1 1 1. And once again, we do Gaussian elimination, and we have this yeah, we have this 1 0 0 minus 3 0 0 and 1 0 0 here. And here we see that both so only P0 here is x1, and so both x2 and x3 are free variable. Okay, so we see here that these two are free variable, free. Okay, and so we can say that as alpha and beta, and x1 is some linear combination between alpha and beta. And so we see that now this null space is two-dimensional space, and our vector can be any linear combination between 3, 1, 0 and this minus 1, 0, 1. Well, with alpha and beta not both equal to 0. Okay, and yeah, so eigenspace correspond to the eigenspace is the space spanned by those two vectors, so, and 3, 1, 0 and minus 1, 0, 1. So we have two linearly independent eigenvectors here. Okay, so it's a two-dimensional space. So two-dimensional space, and if we count the number of eigenvectors, so technically the number of eigenvectors are infinite, and but we will be a bit. So we will say the number of. So I guess let's say number of linearly independent LI, number of LI eigenvectors equal to 2. Okay, so yeah, so usually we'll skip saying the LI part because we know the linear combination always give us another eigenvector. Okay, and yeah, so number of LI eigenvectors correspond to lambda equal to 1 is 2 because we have a two-dimensional eigenspace here. Okay, and yeah, I guess we can have so any questions so far? Yeah, but sometimes we will see that later on we will see that even we have a double root. So here I guess we can be a bit of a spoiler. So we can have a two-dimensional space here because we have a double root. But double roots don't always give you the full two-dimensional subspace. Sometimes you have a double root, but you actually only have one eigenvector, etc. Okay. And yeah, we will talk about that in the later part of the chapter. But for now, let's keep doing calculations. And here is an example where we see we have complex eigenvalues. So we see that actually we have a real matrix, but we can still have a complex eigenvalue because real polynomial can still have complex roots. So we write down the characteristic polynomial. We see that is 1 minus lambda squared plus 4 equal to 0, and the root is 1 plus 2i and 1 minus 2i. So here we have a complex value. Okay. And yeah, so that's a bit unfortunate. So in this chapter, we need to deal with complex value because even we are still focusing on real matrix, we still get complex eigenvectors. Complex eigenvalue, and I think we also get a complex eigenvector. Okay, so yeah, so we need to deal a little bit about complex vector space, even though we don't really talk about it. But when we talk about eigenvalue and eigenvector, even though our matrix is in real, it has a real coefficients, our eigenvectors actually will become complex vectors. Okay? And this makes things a bit complicated because remember when we have a complex vector, its inner product is different. Okay? But anyway, let's do the calculation first. So we can still solve the null subspace here, and so we have this complex. We have this complex Gaussian elimination. It's basically the same thing, just scalars are no complex value. Gaussian elimination is the same, so we don't restate it. Okay, so we do this Gaussian elimination, and we see that we solve for x1 being this vector inside the null space, and it's alpha times this 1 times I. Okay, so you see that correspond to lambda 1 equal to 1 plus 2i. We have this complex eigenvector x1 is this 1i. Okay, and then correspond to this lambda 2 equal to 1 minus 2i. We have this x2 equal to 1 and minus I. Okay, and yeah, so we see that we have these complex eigenvectors. And yeah, we see that even with our matrix has real entries, the characteristic polynomial has a real coefficient, then we still can have a complex root. And but we have some nice property, so the complex root will have will go in conjugate pairs because we have a real coefficient. So if a plus bi is a root, then this a minus bi will also be a root. And we write the complex conjugation in this symbol that we just a bar here. So lambda and lambda bar will both be eigenvalues of A. Okay, and just a bit of a reminder, if let's say x1, if x, y complex vectors, then this x inner product with y will equal to not equal to y inner product with x. Okay, this will be the complex conjugation, and we actually define this as the x vector and times the y vector, and then we need to do two things. We need to do transpose and the complex conjugation. Remember, we need to do the complex conjugation part. Okay, so yeah, that's a bit of reminder on complex inner product, and yeah, that's why we want to say complex inner product, because we actually need to deal with a little bit about complex vector. Although I guess we don't really do inner product between eigenvector that much, but it's still nice to remember the difference between complex vectors and real vectors. Okay, and now let's back to a bit about eigenvalue and eigenvectors. Okay, so yeah, so we have A is a matrix with complex entries. Then we use the bar notation to represent the complex conjugation of A. Just you have AV entry being complex conjugation, and remember, and you can easily derive that this complex conjugation respect the matrix multiplication. So if you can have A times B, then A times B complex conjugation, and I guess it's a bit different from transpose. Then you do conjugation, it's just conjugation A times conjugation B. Then it's different from transpose. So transpose, you have AB transpose equal to B transpose A, but when you do B transpose times A transpose, but when you do conjugation, you don't need to change order. It's just N conjugation times B conjugation. And yeah, and we say that eigenvalues come in pairs, and also eigenvectors will come in pairs. Okay, so if lambda is a complex eigenvalue of your matrix, of your real matrix, and z is the eigenvector associated with lambda, then z bar will be the eigenvector belong to lambda bar, because you can do correlation here. So A times z bar will equal to A bar times z bar, because A is real, so A bar equal to A bar equal to A. And then from the thing we say here, so this A bar times z bar will be AZ bar. And then AZ is equal to lambda z, so this is lambda z bar. And now this is just bar on scalar multiplication, so this is just lambda bar times z bar. I guess you can view lambda as a 1 by 1 matrix and use this again. And so this is lambda bar z bar. And from the beginning to end, you see that AZ bar equal to lambda bar z bar. So lambda bar is, so this is once again our eigenvector equation. So lambda bar is the eigenvalue correspond to z bar. Okay, and I guess this is a good stopping point. and yeah. And yeah, so this is about complex eigenvalue. So real matrix still have a complex eigenvalue and complex eigenvectors, but we have a bit of a nice symmetry here. We have that if A is real, then eigenvalue, then the complex eigenvalue and the complex eigenvectors will come in pairs. So you have lambda is eigenvalue, lambda bar will also be eigenvector, and the eigenvector will, lambda bar is also eigenvalue, and then this is the eigenvector, then the bar will be the corresponding eigenvector. Okay, and yeah, let's stop for 1 minute earlier and see if you have any question. If not, then yeah, then on Wednesday we'll continue more properties about the eigenvalue and eigenvectors. Okay. So yeah, see you on Wednesday.